All right, so let's go ahead and take a look at example number 6. It says a block of mass 6 kilograms is on a frictionless inclined plane, and that's just the way physics people say ramp, but it sounds a little more sciencey, saying frictionless inclined plane that makes an angle of 37 degrees above the horizontal. Calculate the acceleration of the block and then calculate the speed of the block after 1.3 seconds. So before we get going too far on this one, go ahead and sketch this picture into your notes. This is a picture of the setup that's going on. So they basically tell us that there's theta is 37 degrees. It's a right triangle, and then we have a block on this ramp. And then once you sketch that picture in there, we have not done this before, but go ahead and try to do your 5 steps for success since it is a forces problem. And then take it as far as you can take it. And then when you're ready to see how to work through it, go ahead and hit play and we'll be here. All right, so we're back. So step number 1 for success says draw an FBD. So a block on an inclined plane or a ramp is very similar to a block that's just on a flat table. It's just that you've taken the flat table and you've raised it up to an angle to make it an inclined plane. So we're going to come right to the center of this block, and we said there's a force in physics that always acts down, and that's the object's weight. So we're just going to come right here, and we say there is W, going straight down, just like normal. Now the part that's a little trickier on this one, the normal force is perpendicular to the surface. So our surface, this ramp, now has been rotated upwards to make a ramp. So our normal force is actually going to be right here. So here's our normal force. And if I trace this down, that vector should make a right angle with our ramp. So the normal force looks a little different than it did when we had just a block on a flat surface. All right, and then it says it's frictionless, so there's no more forces acting on this thing. So right now, those are our 2 forces, and we'll say step number 1 is done. All right, step number 2. If we go back to the beginning, and I just want to keep doing this just to review, so we have these 5 steps for success. We drew an FBD, so step 1 is done. Now we want to pick a coordinate system based on which way the object wants to move. So this is the time when we have a ramp that our coordinate system is actually going to be different. So up until now, you're like, well, Mr. Dent, why do we even have step 2? It doesn't make sense. But this block wants to move down the ramp. So it's going to make sense to say, well, if the block wants to move down the ramp, let's define that as the positive x direction. Since then when we get a number, we can just say, oh, that's down the ramp, which we've defined as the positive x. And now, since the y-axis is always perpendicular to the x, y is going to be going straight up. So we're just telling who's ever grading our problem here, maybe we're a civil engineer or some kind of engineer and they want to see how we've defined reality. Well, our reality, we've defined it down the ramp as positive x hat, or positive x direction, which we can call x hat. So step number 2 is done. Step number 3. Step number 3 says look at your coordinate system and look at the vectors that you have from step 1 and see if there's any vectors that are not aligned with your axes. So if you have any vectors that aren't lined up, you're going to have to do SOHCAHTOA. So I'm just going to take a peek here. Here's my normal vector, and my normal vector is perfectly lined up with the y-axis, so I don't have to do SOHCAHTOA on those 2. Now let's look at my weight vector going down, and then I'll look at my x-axes, and you can see that those 2 things are not aligned. So that means I am going to have to do SOHCAHTOA on my weight vector going down. And if I'm going to do SOHCAHTOA on my weight vector, that must mean that W is part of a triangle, a right triangle. So what I'm going to do is this. I'm going to say W is my hypotenuse of my triangle, which means that there's 2 legs of this triangle. So I'm going to draw the leg going down like this. And then I'm going to go ahead, we'll draw this one coming over like this. Okay, so basically that vector W, which is right here, here's W. Since that one was not lined up with the x-axis, what I have to do is I have to break that vector W into its component parts, which means it's going to have a part in the y direction going down and a part in the x direction going over there. So you might notice we have a triangle now. So I'm going to put my right angle in here. And what it turns out to be, if you're a geometry all-star as well as a physics all-star, you might start to say, I wonder if that triangle has a 37-degree angle in there. And it turns out that it actually does have a 37-degree angle in there. It's right there. So the theta that's down here, right here, is actually the same theta that is up here. And that's by similar triangles. So I'm not going to take time to show that, but you can kind of look at it and see that you have a triangle that's a smaller version of the bigger triangle. So those would be considered similar triangles, where basically all the angles inside the triangles are congruent with the angles of the bigger triangle. So you don't need to memorize that. You just need to know whatever angle they give you down here for the angle of your ramp is always going to be the top angle of your triangle for your weight vector when you break that up. All right, so that's step 3. You're always going to break up your weight vector when you have a block on a ramp into its x and y components. So we'll put a check right here. Step 4 says add up your vectors in the x and the y direction. So I'm actually going to kind of keep this color coordinated. So I'm going to say sum of my forces in the x. So I'm going to go ahead and look for any forces that are in the x direction. So I look at my normal force first. That's not in the x direction, that's in the y. Now I'm going to look at my w vector, and I'm going to say that is actually going in both the x and y direction. So we had to break it up into its components. This y component would be right here, this green vector. And then its x component is this magenta vector right here. So the only vector that's going in the x direction is going to be this pink one right here. So we need to figure out what that's worth. And to do that, we're going to say, okay, well, we know the hypotenuse is w here, and we know the theta. So we need this opposite side. So I'm just going to do a little side venture up here. I'm going to say the sine of theta is equal to opposite. So that'd be w in the x direction over hypotenuse. So right here, I'm going to call this w sub x because that's the weight vector that's in the x direction. And this over here we call w sub y because that's the weight that's in the y direction. So to get the wx by itself, we do something like this. So if I want the weight vector that's in the x direction, it's going to be equal to w sine of theta. And then somebody out there might remember that, oh, w, that's just equal to mg. So another way you could write this is mg sine of theta. So this pink vector is going to be what we call the weight in the x direction right here. And that's just going to be equal to m times g times the sine of theta. And that's the only vector that's acting in the x direction. So I'm just going to set it equal to m times a times x. And one thing we've kind of realized is it's nice to have an equation for acceleration. So I'm just going to take this a step further now. I notice that I have mg sine theta equals max. And if you have an m on both sides, they cancel because you can picture so you could divide both sides by m. So I'm going to create a nice little equation for us. The acceleration of this block is equal to g sine of theta. So that's the equation for the acceleration of the block down the ramp. So what affects the acceleration is gravity of whatever planet you're on, and then the angle of the incline, which kind of makes sense. Like if you increase the angle, your rate of acceleration should be higher. If you're on a planet with a bigger acceleration g value, then your acceleration down the ramp should be greater. But it doesn't depend on mass, which is interesting because some people might think you'd have a bigger pull going down the ramp if your mass were higher. But with no friction, it's just g sine theta. All right, now let's go ahead and sum our forces in the y direction. So sum your forces in the y. And we're going to say, okay, so we have the normal force, which is right here. And that's lined up with the y, so that one's one of them. And that's going to be a positive normal force. So we'll say that's an n. And now we need to somehow get this force vector right here. So that would be your adjacent side. So I need that adjacent side. I'm just going to call it wy because it's your weight vector in the y direction. So kind of like we did before when we did sine of theta, if we want the adjacent side, we're going to go ahead and do cosine. So at the very top, I'm just going to do another little deal where I say, well, the cosine of theta is going to be the adjacent side, or wy, adjacent over hypotenuse over w. So I'll multiply both sides by w. So we're going to say wy is equal to w cosine of theta. And then we're going to say, oh, but I remember that w is equal to mg. So it's just going to be mg cosine of theta. So I'm going to say minus, because this vector is going down, the wy is going down, mg cosine of theta is equal to m ay. And now in this case, when the block moves down the ramp, it's going to be moving only in the x direction. So that means your acceleration in the y direction is equal to 0. So 0 times anything is 0. So n minus mg cosine of theta is equal to 0, which that means that n is going to be equal to mg cosine of theta. So there's another equation we get from doing our steps for success, number 4. All right, so we did all this, and we haven't actually even plugged any numbers in, which is kind of the nice thing about physics, is right now we just set up the problem. So this is kind of a longer problem, but it's making us tougher. All right, so step number 5 says now we solve the problem using the give and want equation numbers. So I'm going to write out down here givens. So it says, let's go back here. A block of mass 6 kilograms. So that's m equals 6 kilograms. Frictionless plane, angle, theta is 37 degrees. So you better be in degree mode for this one. Calculate the acceleration of the block and then calculate the speed. And the other thing I'm going to say is this block starts at rest, so VO is equal to 0. All right, so what are we looking for? What do we want? It says calculate the speed of the block after 1.3 seconds, but before that it says calculate the acceleration. So we want A. Well, if you go back to all of our old equations, we don't have an equation for the acceleration of a block on an incline like this. So we have to go back up to equation number 4 and look, there's an equation right there. So the equation that we're going to use for this is the acceleration of a block on an inclined plane is just equal to g sine of theta. So it'd be 9.81 meters per second squared times the sine of 37 degrees. And if you crunch that, we should get something like 5.904 meters per second squared. All right, so there's your acceleration of your block. Now notice gravity is 9.81, so it's less than gravity, and that makes sense because it should be accelerating less than the value that gravity accelerates things because it's a block going on an incline. All right, so that's the acceleration, and then it says calculate the speed of the block. So after 1.3 seconds, so you want the v after a time of 1.3 seconds. So we go equation shopping, which you guys all know is my favorite type of shopping. And we're going to use v equals VO plus AT. So VO in this case is 0 plus the acceleration we just found is 5.904 meters per second squared times time, which is 1.3 seconds. And when you crunch that one, you should get a velocity of 7.68 meters per second. So you might think, why would we ever care about a block that's going down a ramp? Well, this applies to any situation where something's going down a ramp or a hill. So imagine this is like somebody sledding down a hill. Imagine this is something, anything that can be slid down a hill, this applies to. The physics is good. So as a kid, I would picture like going sledding on a hill. This is the physics, all of the physics behind why you go fast down a hill that has a bigger incline. So that's a lot of work for one problem. You should feel good after doing that one. That's a good physics problem. So we'll stop there for today. Thanks for watching. Go Physics All-Stars.